afternoon, everybody.
Good morning to you.
Hello. Yeah. Now today you will be on time for dinner, so that's good. Okay. So I promised you that the talks will be sort of independent from each other, and I'm trying to stick to that. So today we have a topic which of course builds upon what we did yesterday, but it's kind of a box which, if you think you got lost a little bit yesterday, there is a chance, that you come back. So what I want to do is the following. So today, the plan is, first of all, I want to restate the strong forcing axioms we formulated at the end yesterday. So we restate the proper forcing axiom, the semi-proper forcing axiom, and Martin's maximum, as well as the double plus versions. I only talked very briefly about the double plus versions yesterday, so I want to expand a little bit on that. So there are double plus versions of all these things, and they are very natural. I mean, don't blame me for the notation. This is just the notation which is in use for these axioms. Okay, then we need to say a few words on iterated forcing. Yesterday we talked just a little bit about forcing, and I didn't say too much because I kind of have to presuppose something, and I hope most of you already saw forcing, and it will be very important when we talk about the consistency of these forcing axioms that we know a little bit about iterated forcing. But if you did not see iterated forcing before, the good news is that there will be something we will be able to take as a black box. So you don't really need to know the proofs, and we're not going to do the proofs. But I will give references in case you're interested. Then there will be, we will need to talk about a relevant concept of an inner model, namely a supercompact cardinal. And in context to that, we will talk about labor functions. Okay, and then we will work towards forcing. Well, we will sort of forget about the proper forcing axiom, and we will work towards forcing Martin's maximum. So what we will actually do is we will look at a proof of forcing the semi-proper forcing axiom, and the same proof actually gives the semi-proper, the double plus version of the semi-proper forcing axiom. And then we will discuss the weak reflection principle, or one weak reflection principle. And we will realize that what we did when we forced the semi-proper forcing axiom, that we actually forced Martin's maximum. Okay, and then at the end of today's lecture, we will show that Martin's maximum implies that the continuum is Aleph2, or, I mean, we already saw yesterday that Martin's axiom sub omega 1 implies Suslin's hypothesis, which says that 2 to the Aleph 0 is equal to 2 to the Aleph 1. Martin's maximum trivially implies Martin's axiom sub omega 1. And so this gives a proof that the continuum, which is equal to 2 to the Aleph 1, is Aleph 2. So it gives a precise value. And as I already stressed yesterday, this also means that you cannot make Martin's maximum stronger by demanding that you meet more dense sets by your given filter. But I will restate these forcing axioms now, and then we will talk about it. There is a chance that we don't get everything done. I'm not absolutely sure. So in case we don't finish today. We will continue with this plan tomorrow. We will have to see how fast things go. And again, I encourage you to always interrupt me and ask questions or make comments as we go along. That would be nice. Okay, is there any question on these kinds of things or on the... Okay, so the first thing is, the first item for today is the restatement of the forcing axioms. Okay. Okay, we can actually start out by restating Martin's axiom sub omega 1. So this is Martin's axiom sub omega 1. And this says that if P has the countable chain condition, so there are no uncountable anti-chains. Okay, the sub omega 1 stands for the fact that you're given at most omega 1 many dense sets. So if D is a family of dense sets, so dense sets in the given forcing P, then there is a filter G which meets all of them, such that G intersect DI is non-empty for all I. Okay, you know what? Let me make a little bit of space because later we will fill in something here. Let me write it here. Then there is a filter G such that G intersect DI is non-empty for all I less than omega 1. Okay? So this is Martin's axiom sub omega 1, from which yesterday we proved that 2 to the aleph 1 is 2 to the aleph 0. Okay, then we were talking about proper forcing, and we formulated the proper forcing axiom. And this is exactly the same statement, except for you relax the requirement that the forcing be CCC to that the forcing be proper. We did not show that every CCC forcing is proper, but that's actually easy. Okay. So same. And again, I want to leave a little bit of space here. Okay. P of A. Same with CCC, replaced by proper. And this is how it goes on, right? So the semi-proper forcing axiom, we talked about semi-proper forcing. So proper forcing was a forcing which does not kill any stationary sets. Stationary sets in the space is x to the omega. Semi-proper, and then we had a reformulation in terms of that for countable substructures of rank initial segments of V, there are generics in the sense as we define them. The semi-proper forcing is something slightly weaker, where you only have semi-generic conditions for such substructures. Okay, so this is the same with CCC, replaced by semi-proper. And finally, Martin's maximum is again the same with CCC replaced by stationary set preserving. And remember, stationary set preserving meant that you preserve stationary subsets of omega-1. Every proper forcing is semi-proper. Every semi-proper forcing preserves stationary subsets of omega-1. Okay, and now, now these are the unplussed versions, and there are versions with a double plus here. There are also versions with 1 plus, but we will not need them. So if I can do 2 pluses here. And then that means that in addition, and I mentioned it very briefly last time, yesterday, not only do you have an omega-1 collection of dense sets, you also have an omega-1 collection of names for stationary sets. So if tau I is such that the empty condition of P forces that tau I is a subset of omega-1, which is stationary, right? So you have a family of omega-1 many names for stationary sets, and precisely in that sense, the empty condition forces that tau I is a stationary subset of omega-1. Then this filter, in addition to meeting all the dense sets, it also has to interpret the names as truly stationary sets. Remember that the filter G is supposed to exist in V. We are not stepping outside of V and going to some generic extension. We stay inside V. So it's some kind of fullness or maximality hypothesis on the universe of sets. We say that, you know, there was this slogan last time, if something can be imagined in a reasonable way, then it already exists. So this is kind of a way to try and spell that out. Okay, so in addition, okay, so this is only a filter, but still a filter can also interpret a name, right? So the interpretation of tau Ig, what is that? This is just the set of all psi less than omega-1, so that there is a P in the filter. It's not a fully V-generic filter, but it doesn't matter. There is a P in the filter so that P forces in the forcing that psi is an element of tau I. You know, this is supposed to be thick in the sense that it's truly stationary. Is stationary. Sorry for my handwriting. So these things are stationary for all I less than omega-1, right? So it could be that the filter, I mean, some psi's might be, for a given I, some psi's might be forced to be in tau I, and even if the empty condition forces that tau I is a stationary subset, it's not necessarily the case that the interpretation of tau I by G is stationary. That's a strong hypothesis. So one can verify, sorry, one can verify that Martin's axiom omega-1 does not imply Martin's axiom omega-1 double plus. And then you arrive at the double plus versions of the stronger forcing axioms by saying exactly this, where you replace or where you relax the hypothesis on the forcing to satisfy the countable chain condition to be proper, semi-proper, or just stationary set preserving forcing, respectively, right? Okay, if one thinks about it a little bit, all these statements are very natural, and I want to restate what we had in the end yesterday, because it will be important when we talk about forcing Martin's maximum. Okay, so I want to say, let me just restate Martin's maximum and Martin's maximum double plus in the way as we did it yesterday. This is not readable. A reformulation of Martin's maximum double plus. I stated the reformulation of Martin's maximum last time. Let's just do it for Martin's maximum double plus. So you can show that the following are equivalent. Martin's maximum double plus. And the second statement is the following. Okay, let's suppose P. Okay, we're talking about Martin's maximum, so we consider stationary set preserving forcings. Let P be a stationary set preserving forcing. Then let A be your favorite parameter. And last time we said, okay, one can do it for a general parameter, but it's handy to think of models. So let M be a model. So a model has relations and so on, and we want that there are only Aleph, at most Aleph1, many of them. So the signature has to be of size at most Aleph1. Okay, then there is a sigma 1 formula which you can force to be, let phi be sigma 1. Okay. And suppose it can be forced, or the forcing P forces that phi holds true of M. Now, yesterday we only stated Martin's maximum and not the double plus version. If you want to get an equivalence of Martin's maximum double plus, we need an additional predicate for the non-stationary ideal. So NS sub omega 1 is the collection So it's the collection of all sets which are non-stationary subsets of omega 1. We will talk about this object for quite a while tomorrow and the day after, and in the rest of this series. It's a very important object. So what I mean when I write NS sub omega 1 here, look, if you force with P, you're not going to change the meaning of, or the answer to a question whether some subset of omega 1 which exists in the ground model is stationary or non-stationary. But there may be new subsets of omega 1 in the extension, so there is a new version of the non-stationary ideal in the extension of the collection of non-stationary sets, right? So what I'm saying is that the collection of non-stationary sets of the extension intersect V is just the collection of the non-stationary sets in V. This is true because by hypothesis the forcing is stationary set preserving. Right. So this is another way to write down the fact that the forcing is stationary set preserving. Okay, this is just a side comment, the thing which is in the box. Okay, so we have a stationary set preserving forcing. We have a model M. We may think of the model as big. We may think of the model as being transitive. A signature at most size Aleph1, phi is sigma 1, and we suppose that it's forced. Then in V, and I wanted to stress when I write NS sub omega 1 here in this formula, it's the version of the non-stationary, of the collection of non-stationary sets in the extension, right? So this is what NS sub omega 1 means in this line here. Okay, then in V, there is a J. And it's elementary. So in other words, you have a substructure of M. So as we discussed yesterday, M might have constants for your favorite Aleph1 many elements of M, and then all these things would have to be in the range. So for instance, if M is transitive and it has size at least Aleph1, you can always make sure that J has omega1 as a subset of the range, for instance, so that the critical point is up high. Okay, then in V there is some elementary embedding J from some M bar to M, and phi of M bar holds true, but now again we have the predicate for the non-stationary ideal. So in V, the sigma-1 statement holds true not necessarily about M itself, but about a substructure of M of size Aleph1. And again, with a predicate for the non-stationary ideal. Okay, and I gave a reference for that. At least I pointed to a paper. I was told that the number of the theorem is not quite correct, but the paper is correct. So there is the proof is not difficult. And this is how we want to think of Martin's maximum, okay? This is an equivalence. So in some sense, so for instance, in order to get acquainted with this kind of statement, for instance, if the model M has size Aleph1 or at most Aleph1, right? I said that we can add constants for Aleph1 many elements. So if M itself has size Aleph1, we can just add all the elements of M as constants, and then the embedding J will have to be just the identity. Okay, so if M has size Aleph1, what it means is if you can force a sigma-1 statement about M, then this sigma-1 statement is actually already true in V, right? So this is some kind of sigma-1 absoluteness, okay? And in fact, this statement where you only talk about M's which has size Aleph1, if you restrict the statement 2 to these kinds of M's of size Aleph1, then this is equivalent to what's called bounded Martin's maximum double plus. But I decided not to talk about the bounded versions of our forcing axioms because, well, we should pay attention to certain things and we cannot talk about everything. Okay. So I would like to ask you to keep in mind this equivalence because it's going to be important for what we are going to do in the rest of today's talk. Is there any question on this statement? So if not, let's move on to the next topic in my list of topics for today. So this is, I said I want to very briefly talk about iterated forcing. Right. So iterated forcing is the following concept. I mean, if you imagine you want to force, for instance, a version of Martin's axiom or one of these strong forcing axioms, we just saw that you can rephrase these forcing or let's say Martin's maximum as a statement that if you can force a certain sigma-1 statement, then a version of that is already true. So it's some kind of, it expresses some kind of saturation of the universe with respect to certain objects. Okay, so there is a natural attempt to show that these axioms are consistent by just, you have a certain sigma-1 statement which you can force. Okay, so force it. And then there is a next sigma-1 statement which may be forced. Okay, so force it and keep going, right? So you want to iterate some kind of forcing construction and you have to do something at limit stages. And it turns out that this whole machinery has been developed mostly by Schindler. And then Foreman, Magidor, and Schindler proved the consistency of MM in the way as we are going to do it, but the proof as I will organize it is different to the proof which you usually see in the textbooks. Okay, but anyway, so iterated forcing is the following. So you have so let's start with V. So suppose you have so when I write P, this is also always a partial order. Okay. Okay, and then when we actually force and we add G to be V generic over P, it might be that we consider another forcing Q, which is now in the extension. Well, V and V of G is as good as V as far as the theory of forcing goes, right? So you could have an H which is V of G generic for Q, and so on. Okay, so then the question is, what are we going to do at limit stages? If you think about what you want to do at limit stages, it's better to reorganize the two-step iteration. So this two-step iteration, you can also organize as follows. You can construe it as follows, right? So the Q, which is in V of G, has a name, let's say Q dot in V, right? So this can be also written down in the following way. We can say P is a poset in V, and Q is a name, or Q is given through a name, so that P forces that Q dot is a poset. And then we can define a poset which is called P star Q dot, and it consists of pairs P comma Q dot such that P is in the forcing P, right? And usually you say that the one of P forces that Q dot is an element of Q dot. Okay, what's the order? That's very natural. You say that P prime Q dot prime is stronger in that poset than P comma Q dot, if and only if. So for kind of component wise, so what does that mean? So P prime is stronger than P, and P forces that Q dot prime is stronger than Q dot. Okay, so and then it turns out that when G is V generic for P and H is V of G generic for Q, that sort of the pair G comma H is generic for the forcing which we just wrote down, for the forcing P star Q dot. And when you have a generic over V for P star Q dot, then you may look at the two components of the filter, and you can read off a G which is V generic for P and an H which is V of G generic for the interpretation of Q dot by G. Okay, so in some sense this is just a translation. So what you're doing is you have a two-step iteration. You first force with P, then with a Q in the extension, and you can do it in one step, and vice versa. Okay, and once you understand that you can handle these two-step iteration in one step, you also can see how to pass a limit stage of such an iteration. So in a general iteration, it's just a longer one than just two steps. So if you have a longer iteration, and this is where really the theory of iterated forcing starts. So this is how do longer iterations look like. You have a sequence of iterants, so alpha less than or equal to theta, and the next iterant is always given from the previous one by composing with this star function we just saw, using one more forcing. So you have a sequence of names Q alpha, and now the alpha is less than theta. Okay. So if you're given, so how does this work? So these sequences, in order for it to be an iterated forcing, and you're really, in some sense, only interested in the last component, P sub theta, okay? But you have to recursively define all the P sub alphas for alpha less than or equal to theta. So how does this work? So if you're given, so what are the requirements on this iteration? So if you're given P alpha, and then the next name Q alpha, you construct P alpha plus 1. P alpha plus 1 needs to be the star product as we defined it on the previous page. So it needs to be P alpha star Q dot alpha. Okay, so this is one requirement on this iteration, on this sequence. And the other one is what happens at limit stages. How does P lambda look like? Well, we will say that a P vector, which is just a sequence of PI's, I less than lambda, is in P lambda if and only if Pi forces that Pi is in Qi dot for all I. And usually, okay, this is the minimum requirement you can make. And usually in order for things to work out, and in order that you can prove some iteration theorems, for instance, that iterations of nicely behaved forcings are again nice, you want to impose further requirements. So for instance, what is important for us is something which is called a countable support iteration. So countable support just means that in addition to what I wrote down about P lambda, so this is a restriction on how you form P lambda. So you only take certain elements of the P lambda we had there. Namely, you demand in addition that the set of i's less than lambda for a limit lambda, so that Pi forces, or let's say that if you look at the I, so that Pi does not force that little Pi is the trivial element of Qi, that this is at most countable. And then there is something which is called revised countable support. Which is sort of the same thing. Namely, you say that the I is less than lambda, so that Pi does not force that Pi is 1. Is at most countable well, you know, the thing is that proper forcing, when you iterate proper forcings, the forcings are always proper. I will write it down on the next page. So the meaning of when a set is countable does not change as you go along the iteration. But for a semi-proper forcing, you might actually add new, there might be sets which are big in the ground model, but then you can cover them by something countable in the extension. So what you want is that this set is at most countable as being forced by some pj for a j less than lambda. Okay, so I will now state two iteration theorems, and this is where I said that we can use them as a black box. You don't need to know the proof, you just need to know that it works. And if one talked about it, it would be a series of talks on its own, so I decided to not do it. So there are Schiller's iteration theorems. He has more iteration theorems, but these are one of the most classical ones. There are much more involved iteration theorems for other classes of forcings. So the first one is that if the sequence of P alphas, alpha less than or equal to theta, Q alpha, alpha less than theta, is a countable support iteration such that every Pi always forces that Qi dot, why do I write an I here now? Let's write an alpha. Is proper for all alpha less than theta, then the last forcing is always proper. Obviously, you prove this by induction, right? You prove it by induction on beta less than or equal to theta, that P sub beta is always proper. And the second statement is something related. It's the same for semi-proper forcing. If P sub alpha, alpha less than or equal to theta, comma, Q sub alpha, alpha less than theta, is a revised countable support iteration such that P sub alpha always forces that Q sub alpha is semi-proper for all alpha less than theta. Then the last forcing is also semi-proper. We saw yesterday that a forcing which is proper, well, it's trivial that a forcing which is proper is semi-proper. And I wrote down the statement that every semi-proper forcing preserves stationary subsets of omega 1, which had the same proof as the proof that a forcing is proper if and only if countable substructures have proper conditions. So in some sense, we saw the proof, and a forcing which preserves stationary subsets of omega 1 don't collapse omega 1. So a consequence of that is the important statement that you can iterate proper and also semi-proper forcings in a way that you will never collapse omega 1, for instance. And this turns out to be the key thing when you want to do certain constructions, and also when you want to force the forcing axioms which we are interested in. Okay. So this is what I thought I should say about iterated forcing. But as I said, for us, we don't really need to know the proofs of these iteration theorems. We only need to know that they are true. And we will go ahead and use them. Okay, if there is no question on that part, I will move on to define supercompact cardinals. Before we do that, let me mention, so everything we do today is covered by ℙmax's book set theory. I didn't check the individual pages, it's spread out through the book, but you will have no problems if you are interested in finding the relevant sections. There is a section on proper forcing, on the proper forcing axiom. There is a section on iterated forcing. There is a section on Martin's maximum. So all these things we're going to discuss today are somewhere in his book. But as I said, the proof I will give is organized in a slightly different way. So for instance, now we are going to define supercompact cardinals, but usually the traditional way to define supercompact cardinals is different from how I will define them now. And this leads to the fact that the proofs look different, but it's only different on the face of it, so there is no substantial difference. Okay. So the next topic today is the definition of supercompact cardinals. So this is a large cardinal concept, and rather what's usually called the Magidor characterization. And we will forget about the traditional definition of supercompact cardinals. Okay. So a supercompact cardinal is a large cardinal. We did not talk about any large cardinals so far. I didn't say anything about strengthening ZFC consistency-wise. So this is, I think, the only large cardinals we will deal with really in this series of talks. It's a kind of fairly strong cardinal. It implies that ZFZ is consistent, and much more, it implies the existence of many, many smaller large cardinals. So this will also be a topic by itself. So when we write down the definition now, don't even think for a second, how would you get such a thing? You cannot prove the existence of such a thing in ZFC or any theory which is weaker than that you just state that there is such a thing. So we just have to swallow it. Okay, so the definition I will give is the following. So kappa is supercompact. Cardinal if for all lambda bigger than kappa. So when I write lambda, I mean a cardinal. Okay. And for all x in H sub lambda. So H sub lambda is the collection of all sets which are hereditarily of size less than lambda. Instead of working with H sub lambda here, you could also work with V sub lambda, which is then truly a regular initial segment of the universe. It doesn't really matter. It's kind of a matter of taste if you work with the H hierarchy or with the V hierarchy. sometimes a little bit more handy to work with the H hierarchy. There is some lambda bar less than kappa, also a cardinal, and some elementary embedding J, which goes from H sub lambda bar to H sub lambda, such that two things are true. There is a critical point of this embedding, and the critical point is mapped to kappa. So the critical point of J is by J mapped to kappa. I will draw a picture in a second, and X is in the range of J. So the picture is, you give me a lambda bigger than kappa, and you give me some X, which is in H sub lambda, and I have to provide a lambda bar less than kappa, together with an elementary embedding from H sub lambda bar into H lambda, so that the critical point exists and is somewhere down here and gets mapped to kappa. So let's write kappa bar for the critical point of J. And also X has a pre-image X bar, which gets mapped to X. So this is the picture, okay? So it's some kind of reflection or compactness or whatever you want to call it. And this is why these things are called super compact cardinals. So this is the definition we are going to work with. So from this picture, for instance, you can play a little bit with it. And I encourage you at some point to play with the definition by yourself. So for instance, if you have the situation, it's very easy to verify that kappa needs to be an inaccessible cardinal. So kappa is regular, kappa is a strong limit, kappa needs to be bigger than omega, so it's strongly inaccessible, but then it also has to be a Marlow cardinal, and it has to be a weakly compact cardinal, it has to be really, really big, it has to be a measurable cardinal, and so on and so on. Okay, but formally we don't need all this information. It's just if you want to get a better understanding, you should play a little bit with this concept. Okay. Now, why do we introduce supercompact cardinals? It turns out that there is only one known way of forcing the stronger forcing axioms, the proper forcing axiom, the semi-proper forcing axiom, Martin's maximum. No matter if you're interested in the unplussed versions or the plus versions, namely you use a supercompact cardinal and do what we are going to do in the course of today's lecture. So this is why we introduce these cardinals. So they are the key large cardinals to show the consistency of these strong forcing axioms, and the expectation, it's not known to be true, but the expectation is that you actually need a supercompact cardinal to force these forcing axioms. And there is a lot of work on showing that this is really necessary, that a supercompact cardinal is really necessary in order to force the strong forcing axiom. There is a lot of inner model theoretic research going on in this area, but also people who work on forcing try to get information on these kinds of things. Okay, but this is now not our issue today. What we want to do now is force Martin's maximum. So yeah, now I will rename it. I will start with a delta, which is a supercompact cardinal. So let's suppose delta is a supercompact cardinal. I want to tell you what a labor function is. And if you saw the definition of a labor function before, probably you saw the other definition of a supercompact cardinal, which I didn't even mention, I don't want to mention. And this is kind of the dual version to a labor function, which we will need when we think in terms of our definition of a supercompact cardinal. Okay? So a function f from delta to v delta is a labor function if the following holds true: if for all lambda bigger than delta and for all x in h lambda. So it starts out the same as in the definition of a supercompact cardinal, right? And then you would say that there is a lambda bar less than kappa, and there is this elementary embedding, and x is in the range. So we will have the same thing, except for we actually have more. So there is an alpha less than delta. And some elementary embedding, J, okay, what do I want? What I really want is that the labor function, so f of alpha, alpha is less than delta, so f of alpha is defined. And what I want is that f of alpha is actually a pair. And the first component is an ordinal, or a cardinal rather, less than delta. And the second component is just an element of h sub that cardinal. And then that we have the thing like in the definition of a supercompact cardinal. Okay, so we have an elementary embedding from h sub. So you have f of alpha, and we have the left component of that pair into h lambda, which maps f of alpha 1 to x. And we have the things as we had before, that namely j of the critical point of j is equal to kappa. Okay, so implicitly when I write down these things, what I want is that f of alpha is an ordered pair. So this is part of the requirement. So there is some alpha such that formally I would say f of alpha is an ordered pair. Lambda bar, x bar, right? And we write lambda bar as f of alpha 0. So this is the left component of the ordered pair. And x bar is f of alpha 1. This is the right component of the ordered pair. Okay? So you want to have this thing. And I want to prove that there is always a labor function. So there is a theorem, I guess by labor, except for that he worked with the other definition of a supercompact cardinal, I think. So there is a labor function. So let's look at the proof. This is just a recursive construction. Let me give the proof. Proof of the existence of a labor function. You just do the most primitive things which you can imagine. So remember that we want to get a function from delta to v delta with the properties we had on the previous slide. Okay, so you just do a recursive construction. So recursively construct f of alpha where alpha is less than lambda, right? So suppose f restricted to alpha is already given. Okay, then what you say is you let f of alpha be some pair lambda bar and x bar such that basically such that there's the situation we had on the previous slide does not exist for the function so far, but now you are at alpha and not at the final point delta, right? So what you want to say is such that there is no beta less than alpha with an elementary embedding J, and I'm pretending that f of beta is an ordered pair and I have a left and a right component. If you know, if that's not true, then the beta is also not valid. Okay. So without loss of generality, all the range of f will consist of ordered pairs. So J goes from H sub f of beta, left component of that, into H lambda bar, and f of beta 1 by this map J goes to x bar. And I pick lambda bar to be least such. Okay, so when I define f of alpha, I wonder if there is a pair lambda bar x bar, so that I don't have a beta less than alpha with this situation. Okay, and then I pick the least lambda bar and I pick some x bar. The x bar needs to be an element of H lambda bar, so that there is no such situation. Notice that f of beta, because beta is less than alpha, all these things are defined, so I can ask this question, right? Okay, so this ends the definition, and now you just have to see that it works. This works, and this is just a reflection argument. It's a little bit strange that you have this complete freedom in the choice, right? Okay, we minimize the lambda bar, but we just pick some x bar. You could work with some well ordering of H sub delta or something, which is the same as V sub delta, and pick the least one, but it really doesn't matter which one you pick. This is a bit odd. Okay. Okay, so this works. So otherwise, there is a counterexample. So there is a lambda bigger than delta and some x in H lambda. Be a counterexample. Okay, the trick is simply the following. Maybe I should draw a picture and then leave the details to you to fill them in. So what we're going to do is, look, you have delta here. You have x here, right? So there is this counterexample. Okay, so let's put everything into some. So there is lambda here. So let's look at a slightly bigger structure, H sub capital omega, which can see everything. So it can see in particular H lambda, it can see X and so on, okay? Now by the definition of supercompactness for this whole situation, there is a capital omega bar, which is smaller than delta, together with an elementary embedding whose critical point sends some delta bar to delta, and you have a lambda bar here, and you have an x bar here. We may throw in lambda and x into the range. X bar gets mapped to x. Okay. Okay. So what does that all mean? So lambda and x are a counterexample to the fact that the function which we defined does it. Okay. But h sub capital omega can see all of that. Okay, it can see that the pair lambda comma x is a counterexample. So just by elementarity, h sub capital omega bar can see that the pair lambda bar x bar is a counterexample. Okay. But now it's a counterexample. So we have that from this we get, I called it, let's see, this is a delta. Can I rename it and can I call it alpha? So alpha is here, this is x bar. And this thing is lambda bar, right? So just by elementarity, f of alpha is defined. Okay. And then from that you get an easy contradiction. Okay, it is defined. So we have the following, that there is no, so h, what does that mean now? So h sub capital omega bar thinks that there is no, that there is no beta less than alpha together with an elementary embedding k from h sub f beta 0 into h sub f alpha 0, which maps f beta 1 to f alpha 1 with the usual properties. Okay. And then you let and then you shift everything upstairs and you get a contradiction. Okay, so you just let lambda bar and x bar be j of f alpha 0, f alpha 1. And then we have upstairs by elementarity that h sub capital omega thinks, we have this statement over here that h sub omega bar thinks this statement, so h sub omega will think that there is no k from some h f beta 0 to h sub lambda star, so that f beta 1 gets mapped to x star. But this is a contradiction as we have j. Right, the model H sub capital omega can see J, it can see everything. J is small, so it can see it. This is how we pick capital omega. And lambda star and x star are in the range of J, so this gives a contradiction to the existence of J. Okay, so this is not a hard argument. So the construction of the labor function is kind of primitive and it all works out nicely. So there is a labor function. What is the point of a labor function? The point of a labor function for our purpose is that it gives us a way to organize an iteration, and this is what we are going to do right now. So I think what I can do before the break starts is I will give you a proof of the semi-proper forcing axioms modulo all the black boxes we introduced, and then after the break we will discuss why we actually got a model of Martin's maximum. Okay? So we have the floor. Yes, of course. Oh, now you're very difficult to understand. Why is?
Why f is in h comma bar? How you define that? I mean, what is f? You are defining f by induction, right?
That's true. Yes. Yes.
And you should have f up to some point in h comma bar. I am a bit confused.
Gamma bar, you're saying? I'm sorry?
Why your construction of f is in h comma bar? Why is it in h comma bar?
What is gamma bar?
I mean, sorry, omega bar.
Oh, I see. That's okay. Let me. We have this, right? We have this. There is this x, which is a counterexample. Lambda and x is a counterexample. But everything is in h sub capital omega. You just pick capital omega big enough so that it can see everything. It's a construction.
But why it is in h omega bar? Because you said that h omega bar thinks that there is no beta less than alpha such that.
Oh, you want? Is your question why is f in the range of J? Is that
f is in range f, but I think you should find the preimage of f. Could you go to the previous page?
No, unfortunately not, because
okay.
I don't know how to do such a thing. I erased it. I will have wait. I can.
At some point, you write that you wrote there is no beta less than alpha with some j from. Sorry, just let me say.
Yeah.
You said that h omega bar thinks that there is no beta less than alpha and an elementary embedding k from h of f beta. This f, I think, should be f bar, should be preimage of f, no?
Yes, yes, of course. But okay, so for one thing, f, you know, by the definition of supercompactness I gave, of course, not only can we put x and lambda into the range of J, also f is in the range of J, right? So that
yes,
that's
f
clear.
is in
Okay.
range. That's right.
But now, right? Yeah. Wait a second. And now, okay. So f has a preimage, but what's the preimage of f? The critical point of the embedding is alpha, right? So the preimage, if this is J, so J to the -1 of f is simply f restricted to alpha, right? And when you write down what you just wrote, it's true what you say. I said, we are talking about betas less than alpha and f of beta. Formally, I should write f restricted to alpha of beta or j to the -1 of f at beta, but that's the same as f of beta, right?
Okay,
so,
okay, right. Thanks.
Right? So for beta less than alpha, j to the -1 of f at beta is the same as f restricted to alpha at beta, and that's the same as f of beta. Yeah. And this I implicitly used in what I wrote down before. Okay?
Okay, thanks.
Okay, great. Great. Okay. Yeah, I don't know how to, I don't know, I have to figure out a way to scroll and I couldn't make it. I don't know. Okay. So actually the proof of, so I was about to write down the theorem by Foreman, Magidor, and Schindler. Yeah. That if delta is supercompact, then the semi-proper forcing axiom holds in a generic extension, and the proof gives much more information. Okay, so the proof more or less just puts together everything we discussed so far. So what are we going to do? So we define an iteration, define a revised countable support iteration P alpha, alpha less than or equal to delta. This is the supercompact cardinal, comma, Q dot alpha, alpha less than delta. So this is an iteration of length delta, such that an iteration of semi-proper forcings okay. So what does it mean to be an iteration of semi-proper forcings? This is exactly like in the hypothesis of the second iteration theorem of Schindler. So what we really want is that for every alpha less than delta, P alpha forces that Q dot alpha is a semi-proper forcing, right? So, and then by the iteration theorem, we will know that P sub delta is actually a semi-proper forcing, okay? So how do you pick the individual forcing? So this is where the labor function guides you. Let F, oops, let F be a labor function. So you fix it. Okay. So what you say is at stage, so we do it recursively, right? At stage alpha, so now we have to pick a forcing. So you force with, I mean, when I say force with Q alpha, I mean, what is the Q alpha, right? So the Q alpha is equal to, okay, you simply look at the labor function. What does the labor function tell you? It gives you, typically it gives you a pair. So there is a left and the right component. The left component we said is a cardinal less than delta. The right component is just some object. So the right component might be a semi-proper forcing, right? So force with the right component of what the labor function tells you, provided P alpha forces, or it's true in the forcing extension, that you know what? For technical reasons, I don't want to really look at the right component. I want to split the right component again into two parts. So it could be that the right component again is a pair. And then what I want to do is I want to take the left component. But this, you don't have to worry about these technical details. Okay, so there is a canonical component of what the labor function tells you, and you force with this canonical component if and only if it's forced by P alpha that this canonical component is a semi-proper forcing. Okay. Okay. And otherwise, if that's not true, you just collapse. Otherwise, you force with the collapse of, let's say, f alpha 0. That's always a cardinal less than delta, and you want to collapse it to omega 1. This is always a this is a sigma closed forcing, so it has all the nice properties we want of our forcings. Okay. Now we have a quarter of an hour left until the break, so let me, right, so this is a very easy way to define an iteration. So modulo everything we discussed today, everything is fine, so this is a very nicely behaved iteration. So the iteration is semi-proper because we only use semi-proper forcings. And what we want to verify now is that the semi-proper forcing axiom holds true in the extension. And we actually want to verify not the formal statement of the semi-proper forcing axiom, but we want to verify the equivalent formulation of the semi-proper forcing axiom in terms of that a sigma 1 statement about a model, if it can be forced, then it's already true about an Aleph one-sized substructure. Okay, so how does this go? This is very, very easy. So verify that the semi-proper forcing axiom holds true in the generic extension by the last forcing, delta. Okay, so maybe we should write let G be V generic for P delta. That might be convenient. Okay, so how does this go? So let me draw a picture. So what do we have to verify? Right, we are given a model M in VG of arbitrary size, but the signature is at most of size Aleph 1. Okay, and we need to verify that if phi is a sigma 1 statement, so we have a forcing, let me call it P, okay, we want to verify the semi-proper forcing axiom, right? So we suppose we have a forcing P which is semi-proper in V of G. Phi is a sigma 1 statement, and P forces that phi holds true of M. I'm showing the unplussed version of the semi-proper forcing axiom. It will turn out that the very same argument shows the double plus version. So the phi could also have a predicate for the non-stationary ideal, no problem. Okay, so we want to see well, let me not write it down, let me just say it. We want to see that there is an elementary embedding J from M bar into M, so that phi of M bar holds true, right? This is what we want to see. Okay. So we may throw everything into, you know, there is some, let's pick some large lambda so that the model M is an element of H sub lambda, and also P is there and everything, okay? There is this delta, because we keep collapsing, it's not very hard to verify by genericity and by how the iteration is organized that we keep collapsing cardinals below delta to omega 1. And it's also important, this is something we also didn't do, is to show that these revised countable support iteration has the property that the whole iteration P delta has the delta chain condition. So everything below delta will be collapsed to omega 1, but delta itself is not collapsed. So delta will become the omega 2 of the generic extension. Okay, so you pick a lambda big enough, and now for a moment you work in V. So you apply not exactly the Magidor definition of a supercompact cardinal, but actually the, we have this labor function. Okay. So what we do is we pick, and we have M and we have P, but we also have names for M, and we have a name for P, right? So what we do is we pick according to the property of the labor function such a situation, right? So we have an alpha, we have an M bar or dot, which is actually let me see. What I want to do is the following, namely that we want to have that lambda comma P dot bar comma M dot bar is equal to the value of the labor function at alpha. And we have this picture, right? We have a J which sends H sub lambda bar to H sub lambda, and it sends the pair P dot bar comma M dot bar to P dot comma M dot. So this is now in the ground model D. Okay, and this thing is the value of the labor function at alpha. So this all can be chosen. Okay, so this gives an elementary embedding from H lambda bar to H lambda, but it can be extended. We have the generic G. So down here we have the generic G restricted to alpha. So this J can be lifted to an elementary embedding J hat from H lambda bar at join G restricted to alpha to H, H lambda G, so that's a rank initial segment of the forcing extension, so that right, so that the interpretation of this thing by G restricted to alpha and the interpretation of this thing by G restricted to alpha gets mapped to, well, M dot was the name for M and P dot was the name for P. So it gets mapped to P and to M. Okay, so this is our picture now. And now, if you put everything together, what does that now mean? At stage alpha, when you define the forcing iteration, at stage alpha, you were wondering if f of alpha has a right component whose left component is a semi-proper forcing. But that's exactly true here now, right? So if you look at f of alpha, the left component of the right component is the name of a forcing. And just by elementarity of J hat, it's true that in the forcing extension by G restricted to alpha, the interpretation of P dot bar by G restricted to alpha is a semi-proper forcing. So in other words, at stage alpha, you use exactly that forcing to continue, right? Okay, but upstairs, also by elementarity, upstairs you have phi of M holding true in V of G. So you may pick lambda big enough so that it can see that phi of M holds true upstairs. So just by elementarity, using the elementarity of J hat, we have that that downstairs H lambda bar G alpha thinks, I'm sorry. Upstairs, I misspoke. Upstairs, we have to look at this now. So P forces that phi of M holds true. So downstairs we know that P bar forces over H lambda bar G of alpha that phi of kind of M bar holds true. Okay, but P bar is the forcing which we use at stage alpha, right? So what we can say is that H lambda bar adjoint G restricted to alpha plus 1 forces the sigma 1 statement. But it's a sigma 1 statement, so once it's true, it stays true forever. Okay, and it's also upward absolute. So from this all, because we forced with P bar at stage alpha, we can conclude that in V of G, phi of M dot bar interpreted by G restricted to alpha holds true. Okay, but now we have exactly the situation we wanted to verify. We assume that we have the semi-proper forcing P, which forces phi of M, and we concluded that already in V of G, there is this substructure M dot bar interpreted by G restricted to alpha, which can be embedded by J hat into M, and the sigma 1 statement phi holds true about it. So J hat can be seen in V of G because J was picked in V, and then the extension J hat just exists in V of G. So everything's fine. Okay, so this is the entire proof, and we are just on time now for a 15-minute break, or maybe 3 more minutes. Okay. Okay. So what did we do before the break? We defined the concept of a supercompact kernel. And if delta is a supercompact kernel, we showed that there is a revised countable support iteration of length delta, so that in the forcing extension, the semi-proper forcing axiom holds true. Well, we use the, we didn't give too much detail on the proof, so there are certain things you have to go through in order to verify that it's really true, but I gave you the kind of some of the key steps of the argument. So it's of course not a complete proof, but I think it gave you a flavor of what's going on, and I think I gave you enough of the argument so that you could now go and verify the details. I was asked if there is any place where the argument we just gave is written down, and the answer is I don't really know if exactly that argument is written down, unfortunately. So now what is the next goal? What we said, we are really interested in double plus, and it will only come out later why we are really so much interested in double plus. I mean, for one thing, it's the strongest forcing axiom in our list of forcing axioms which we have provided, but also, as a matter of fact, double plus is interesting because it connects with Woodin's axiom star. I want to talk about the next days, in that double plus implies star, and this is something which is sort of our goal, even though I don't know if we will be able to squeeze in the proof of that. We will have to see. Okay, so the first issue now is there are two issues left. One, how about getting from the semi-proper forcing axiom to Martin's maximum, and the other issue is how to verify the double star versions. The latter is easier. The double star versions, if you just take another look at the argument of what we did, you realize that we actually verified the double star version. Why is that? Maybe it doesn't hurt if just by a picture I repeat the argument we just gave before the break. Okay, so it turns out that in the model V of G, which was the forcing extension of V by P delta as being defined before the break, we verified that we have the semi-proper forcing axiom, but we actually have the double plus version, and it's the very same argument. So let's take another look at this argument and verify that you have the double plus version. Okay, so what do we need to do for the double plus version? So the iteration had length delta, and we said that delta will become the omega 2 of the forcing extension by the iteration. So we, in order to verify the double plus version, we are given a model M in V of G. So we put N into H sub lambda of the forcing extension. Okay. And maybe let's now take some theta, which is large enough so that H theta of the forcing extension can see everything. Okay, so the hypothesis now is that there is this forcing P, which is semi-proper, and it forces that a sigma 1 statement phi holds true about M, but there is also a parameter for the non-stationary ideal floating around. The parameter for the non-stationary ideal in the sense of the forcing extension. Okay, and now we have to verify exactly what we did before, but it's exactly the argument as before. Okay, so we pick by the definition of the labor function, and maybe I don't have to write it down all again. We can pick in V a situation that we have an elementary embedding from some, yeah, okay, so there is a theta bar here. So in V, there is an elementary embedding from H theta bar to H theta, which has all the relevant objects in the range. And the pre-images are actually given by the value under the labor function, exactly as we had it before. So what did we have before? So there is this G restricted to alpha here. There is a lambda bar here. Okay. If you are in V, there is the name for M, there is a name for P. You have M dot bar down here. You have P dot bar down here. Okay, and we have everything like before. So we had this map J hat, which goes from H theta bar restricted to, not restricted, I'm sorry. H theta bar at join G restricted to alpha to H theta of G. Okay, and M bar, the interpretation of that gets mapped to M. Okay, and this guy gets mapped to P, but this is also as being given, well, in the end, this is just the forcing we do at stage alpha. So this is Q alpha. Okay. Well, formally, there is no Q alpha, so I should write Q alpha dot is actually equal to P dot bar. Okay, so this is the key thing. Okay, but morally, P dot bar interpreted by G restricted to alpha is the forcing we do at stage alpha. Okay, and then again, just by elementarity. So we have that P forces this sigma 1 statement upstairs. So we have that, over, so P dot bar interpreted by G restricted to alpha forces over the model H theta bar adjoint G restricted to alpha, just by elementarity that phi holds true of M dot bar interpreted by G restricted to alpha, comma, the non-stationary ideal at omega 1 of the model H sub theta bar adjoint G restricted to alpha. So this box follows from the box up here just by elementarity. And now the only thing which, now before we said, before there was no predicate for the non-stationary ideal. So then we just said, okay, phi is a sigma 1 statement. And it's, for one thing, it's upward absolute. So the fact that it holds true in H theta bar adjoint G restricted to alpha means that it's actually true in the intermediate extension V of G restricted to alpha. But then the tail end cannot destroy the truth of a sigma 1 statement because it's sigma 1. So in V of G, the sigma 1 statement is in fact true. But now the only new key feature is that the tail end of the iteration, where the tail end of the iteration from alpha up to delta has the property that we don't kill any stationary sets. So the revised countable support iteration of semi-proper forcings has the property that tail ends of that iteration don't kill stationary subsets of omega 1. So we can run the very same argument. Okay, so by the choice of theta bar and by the fact that phi is sigma 1, we also have that in V of G restricted to alpha, phi holds true of M dot bar interpreted by G restricted to alpha together with a non-stationary ideal. And then the tail end of the iteration going from alpha to delta does not kill any stationary sets, and therefore this statement is also true in the final forcing extension. So the double plus version of the semi-proper forcing axiom follows exactly by the same argument if you take one more look at this argument. Okay, so this dealt with the first issue. Okay, so we have this statement. We have the semi-proper forcing axiom and in fact the double plus version. So now what about Martin's maximum? Okay, there are two answers to this. One answer is that abstractly, the semi-proper forcing axiom implies Martin's maximum. And also the double plus versions imply each other. One implies the other. So they are actually equivalent. But this is not how we are going to do. We are going to do it in the way as Forman, Magidor, Schindler did it originally in the paper, that we verify that a certain reflection principle holds in this particular forcing extension, and we show that this reflection principle implies Martin's maximum. So this we are going to prove a weaker statement, but I just want to illustrate how things are, and this weaker statement is easier to prove. So I decided to do that. Okay. So Forman, Magidor, Schindler actually verified that mm double plus holds true in the model V of G, which was V of U force with this iteration of length delta, which we constructed. Of course, they used this. They used the different proof. They didn't use the. I'm sorry. They didn't use the definition of a supercompact cardinals, which we used, but essentially it's exactly that argument. Okay. I simply find the argument that we gave a little bit more handy. Okay, so that's what we want to do now. And in order to do that, we have to introduce a reflection principle. I think this goes under all kinds of names, and I'm always confused about these reflection principles. So I want to write weak reflection principle at theta for the following statement. Okay. We know what a stationary subset. We know what a stationary subset of. You know, if you look at the space x to the omega yesterday, we discussed quite lengthy what it means for a subset of x to the omega to be stationary. So our x will now be h theta. So I guess we pretend that theta is a sufficiently big cardinal. Okay, if f is stationary, if f is a stationary subset of that, then there is a y contained in h theta as a subset, so that the cardinality of y is equal to LF1. So in order to make sense of that, I think we should say that theta is uncountable, right? So that if you look at S restricted to the smaller space y to the omega, that's stationary. Okay.
Do we also ask y to contain omega 1 as a subset?
I was thinking of it stationary. There is some. Do we need to write this down actually?
Yeah, remember there are wacky counterexamples.
Is that true? I wasn't. I thought that this should work. Let's see. Okay, maybe formally. Okay, probably, yeah. I mean, this is what I have in mind anyway. So I'm not sure if formally. You might be right. Okay, we may assume. We may assume that otherwise, yeah. So let's say omega 1. I don't know.
Yeah, we can also wait and see where it breaks down, if it breaks down at all.
Okay, yes, but you are absolutely right. I mean, this is something we should definitely kind of. Okay,
I think it is not as stated in Yek's book.
That's possible. How is it stated in his book?
exactly like your definition. Of
Oh,
course.
without
Yeah,
the,
yeah,
okay.
without omega.
Yeah, okay. Stationary. You know, I mean, probably you can, you know, if you want to, I mean, probably you can, without loss of correlation, all the elements of S have, no, what am I saying? No, never mind. Okay. Never mind. Okay, this is a detail I will leave to you to figure out, and I can also. Okay, so this is the weak reflection principle at theta, and now what's the role of it? So there are two things. So there are two statements. So for one thing, if the weak reflection principle at theta holds true for all theta, then, so this is the first thing, then every stationary set preserving forcing is semi-proper. So it's kind of, this reflection principle is kind of the natural, if you want, reflection principle, which allows you to prove that every stationary set preserving forcing is actually semi-proper. And then from that, or rather, we will verify in the model V of G constructed before the break, this weak reflection principle at theta holds true for all theta. And the consequence of this is, right, so what does that mean? So if you have a sigma 1 statement, let's say in the predicate for the non-stationary ideal, which you can force by a stationary set preserving forcing to be true over V of G, then because V of G satisfies this reflection principle and therefore all the stationary set preserving forcings are semi-proper, there is actually a semi-proper forcing which makes this sigma 1 statement about the given model true. And then we argued that that there is actually this substructure, and the sigma 1 statement actually holds true in V of G already. So in other words, we just verify that MM double plus holds true in V of G, right? And I have to say that this is the only known way to verify, to show the consistency of a statement like Martin's maximum. What you would like to do is, you could try to do it kind of more directly and not going through some of these reflection principles. So why not simply saying, okay, instead of iterating semi-proper forcings, why don't I just iterate stationary set preserving forcings? It is very delicate because when you are in a world where where this reflection principle is not true, or let's say that its consequence is not true, then it might be that you iterate stationary set preserving forcings, and in limit stages you actually, for instance, collapse omega 1, and then the whole thing breaks down. We didn't really see why this is important that you don't collapse omega 1, but it is true. So there are actual counterexamples, there are actual examples constructed by Schiller and others of iterations just of length omega, where you iterate stationary set preserving forcings, and at the limit stage, no matter how you define the limit, you will collapse omega 1. So it is a very delicate issue, iterating stationary set preserving forcings. So the way out here is that when you construct a model of MM, you first just forget about stationary set preserving forcings and you just iterate the smaller class of semi-proper forcings, and then you verify that in the end, mysteriously sort of, you have the stronger statement that you have the forcing axiom actually also for stationary set preserving forcing. So this is the only known way, and this is how we have to live with. Okay, so we have these two statements, and I sort of want to verify both of them. But not really fully verify. I want to indicate why this is true. As I said, everything we do today is in Yek's textbook, so it's nothing new. We also want to move on towards less well-known stuff, even though all these things maybe for some of you are not well-known, but I want to also do other things. Okay, so what are we going to do first? So let's first prove B. Okay, so let's verify that in the model we have this reflection principle. The weak reflection principle at theta holds true in our model V of G, which was obtained by this semi-proper iteration up through a supercompact kernel. Okay, so what's the idea? I just want to give you the idea how to verify it, and it's really very easy to fill in the details then. So the idea is you are given a set S, which is a subset of h theta to the omega. Well, okay, now we have to be a little bit careful. Let me write it down correctly. So we are in V of G, and I don't want to confuse things now. So what is a typical h theta of V of G? Well, I can also write it at h theta of the ground model adjoint G. So this is the same as the h theta of V of G for a theta bigger than delta. Right, okay, so we have a set S, which is a subset of that thing. It exists in V of G and it's stationary there. Okay, we pick a theta, maybe we also pick some capital omega, which is bigger. You know, we do the usual game where we exploit the fact that we did our iteration with the help or via the use of this labor function. So we have delta here. This. I want to make delta a bit bigger. So we have this picture. So in V, we can take this thing according to the definition of the labor function. So what do I actually want to make use of? What I want to say is that we may look at the collapse of theta or h theta or something down to omega 1. This is a sigma closed forcing, and therefore it has all the properties we want. So it's even proper, it's semi-proper, it preserves stationary sets. Okay, and we can pick things in a way, we can pick this picture in a way that the forcing at stage alpha is actually the collapse of the pre-image of theta to omega 1. Right, so omega 1 is down here somewhere. It's not moved by this J, right? So I want to have that that basically Q alpha, or formally Q alpha dot, is equal to call omega 1 H sub theta bar dot. Right? So basically the forcing at stage alpha, I can say, is this one particular forcing, right? Okay, and then we may verify that just by elementarity, so upstairs, you know, the H omega thinks, not H omega. H omega adjoint G thinks that S is stationary, a stationary subset of H theta of G to the omega. So just by elementarity, H, there is an omega bar here, G restricted to alpha, thinks that the pre-image of S, which is S bar, is stationary. We can pick things in a way that there is a pre-image and so on, right? Just by the use of the label function. So S bar is the pre-image of S. So where is S? S is somewhere here. And there is an S bar here. And this S bar gets mapped to S. Okay, now the fourth thing which collapses H theta bar to omega 1 is actually proper. Okay, so that means that if you do the next step of the iteration, which is the use of the collapse of H theta bar to omega 1, it does not kill the stationarity of S bar. Okay, okay, so we have that, okay, this by the choice of capital omega and then of capital omega bar, we have that V of G restricted to alpha thinks that S bar is stationary. But then by what I just said, we actually have that the next step of the iteration does not kill the stationarity of S bar. Okay. And this means that actually, what's happening now? We have S bar as a stationary subset of, S bar is a subset of H. This is a subset of H theta bar of G restricted to alpha to the omega. But this whole object, H theta bar, gets collapsed to omega 1 in the alpha step of the iteration. So this object will become an object of size aleph 1. So there is a bijection of this object H theta bar adjoint G restricted to alpha with omega 1 in the extension in the alpha plus first model from the iteration. And therefore the stationary, you can construe the stationary subset S bar as actually a stationary subset of omega 1, right? Modulo this bijection with omega 1, it becomes a stationary subset of omega 1. And then I already mentioned before that tail ends of semi-proper iterations don't kill stationary subsets of omega 1. They may kill general stationary set, but not stationary subsets of omega 1. So that means that in the final extension, V of G, S bar is still a stationary set. Okay, that's great news because now we look at the map J, and we saw that there is this lift of J to a J head from H theta bar at join G restricted to alpha, not theta bar I want to write in a capital omega bar here into H sub omega adjoint G. Okay. So the set S bar exists in this model downstairs. So we may look at J head, the pointwise image of what is it? Of S bar. And it turns out that this, because S bar is in the final model V of G a stationary set, that this thing is also stationary, that this is a stationary subset. Well, of what? Well, it is stationary, but of what? What is the relevant Y as in the definition of the weak reflection principle? You just take the J head of H theta bar adjoint G restricted to alpha. So this is your Y. Okay, so we have exactly what we want. So we start out with a stationary subset of H theta, or of H theta of the generic extension, like up here. Okay, and we found a Y, like down here. So that, and what is this thing? What is the pointwise image under J hat of S bar? It is just, you know, now I'm like, I have a lack of space somehow. J hat of S bar is simply S restricted to Y to the omega, if you look at things. Okay, so we verified exactly what we want. So we verified that this, all these reflection principles with the parameter theta are true in our given model, and then let's verify the statement A. So this was B, as defined on the previous slide, and let's turn to A. So the weak reflection principle at theta holds true at theta. Holds true for all theta. This implies that every stationary set preserving forcing is actually semi-proper. By the way, this statement, which I now put into a box, is often abbreviated by a dagger. So dagger is this very statement. Okay, so here is a brief sketch of this argument, and I want to finish it in a couple of minutes because we also want to talk about MM implying that the continuum is of size Aleph2. Okay, so so fix a forcing which preserves stationary subsets of omega 1. So let me show you what you do, and then you can go back and put in all the details of the argument. So suppose P is not semi-proper. Okay, what does that mean? You know, we have to verify that basically for sufficiently large theta, if you take any countable substructure X of H theta and the condition in that substructure in the forcing, then it can be extended to a semi-generic condition. So if that's not true, and it was also mentioned yesterday, that this is equivalent to verifying that this holds true for a club. You don't need it for all substructures, you only need it for a club. So if that's not true, then there is a stationary set for which you cannot pick semi-generics, right? So if P is not semi-proper, so we go for a contradiction, then the set S is equal to the set of countable substructures of some, we pick a large enough theta, so X is countable, and there is some P in X and also in the forcing with no X semi-generic extension, strengthening that this is stationary. Right. So first step is we apply Fodor's lemma, which we showed in the very beginning of yesterday's talk, but to saying that you know, you look at the map which takes such a countable substructure X and maps it to a P with this property with no semi-generic extension. So this is a regressive function, and then on a stationary subset you can stabilize this P. So we have, there is a T subset of X stationary, so that there is one P in the forcing, so that P is in X for all X in T, and there is no X semi-generic extension of P for all X in T. Okay, and now what you do is you simply say, okay, by the weak reflection principle at theta, you know that there is a Y subset of H theta of size LF1 such that T restricted to Y to the omega is stationary. And now what you just do is so there we have this one constant P up here, this one condition, so that for no submodels in capital T there is a semi-generic extension. So what we now do is we simply pick a V generic which contains this condition. So we pick a G V generic for the forcing P with P in G. Okay. So the forcing P preserves stationary subsets of omega 1. And kind of the point is that we found a stationary, we found a restriction of T to a set of size LF1 so that we can kind of construe this restriction T intersect Y to the omega. This is kind of a stationary subset of omega 1 now, so we preserve its stationarity. So what we can actually find is, because P preserves stationary subsets of omega 1, when I write it preserves stationary sets, I mean it preserves stationary subsets of omega 1. This implies that we find an X which is in T and also in Y to the omega, such that X of G intersect omega 1. What is X of G? So this should be a little x. This is the same X as this X. So X of G is just the set of all tau G, the interpretations of all names which happen to be in the substructure X. And I can find it in a way that X of G intersect omega 1 is equal to X intersect omega 1, and this I want to call alpha. The set of basically the set of X's which have this property, this is a club, and there, because T is still stationary, I can find the situation in the extension where this is true. Okay. And then you will have that in V of G, if you take a term tau, a name in the forcing for an ordinal, for a countable ordinal, then T of G must be by the, by the setup, because x of g intersect omega 1 is the same as x intersect omega 1. So Tg is always less than alpha for all tau in the substructure, a name for a countable ordinal. Okay, so you have this key thing. But then the final argument, the final step is, this is a property about the forcing extension, so it has to be forced by something. So this has to be forced by a condition, and then it turns out that this one condition which forces that, this is actually semi-generic for x. So it's x semi-generic, but x is in T. So there was supposed to be no semi-generic. So that's a contradiction. So this is forced by a condition. So this is forced by some Q, and we may, with a lot of generality, assume that Q is stronger than P. And that's a contradiction, because then P has a X semi-generic extension, even though X is in T. Okay? Okay, so this is a sketch of this argument. So we verified the following. We showed directly that using a super compact cardinal, you can do an iteration of semi-proper forcings, which forces the semi-proper forcing axiom and actually the double plus version. And then we verified that in that model, we have these reflection principles for every theta. And abstractly from the reflection principle, you can verify that Martin's maximum, that every stationary set preserving forcing is actually semi-proper, and then we have full Martin's maximum double plus. One doesn't have to do that way, I said. One can verify directly by a more complicated argument that the semi-proper forcing axiom implies this weak reflection principle. And then one can say abstractly, it's not even true in this particular model. It's not a peculiar feature of this particular model that every stationary preserving pose set is semi-proper. It's just generally true under the semi-proper forcing axiom. But we didn't do it that way. It's easier if you do it the way we did it, and this suffices for our purposes here. So in sum, we verified that Martin's maximum double plus is consistent, right? Now I'm confused. I have, how much time do I have left? I have 3 quarters, yeah. 3/4 of an hour. Right?
45 minutes left.
45 minutes, yeah, okay, oh, that's perfect, okay. I hope you guys are not yet falling asleep. Okay, so to sum, in sum, so if we step back a little bit, to summarize, this is not English, I don't know. To summarize, right? So we said that if delta is super compact, we designed this iteration of length delta so that in V P delta, we have the semi-proper forcing axiom double plus. We also have the weak reflection principle at theta for all theta. And this implies the dagger principle that all stationary set preserving forcings are semi-proper. And the conclusion was that in here, we have Martin's maximum double plus. Okay. So yesterday, there was the question, why is it called Martin's maximum? So one answer was that if you relax, if you increase the class of forcings further to incorporate also forcings which are allowed to kill stationary sets, then you get a statement which becomes inconsistent, right? So the example was if you have a set S, so that S and its complement is stationary, I mentioned that there is a forcing may force S to contain a club C by a forcing which preserves the stationarity of all stationary subsets of S. So that's kind of still a very mild forcing, but it's not mild in the sense that the stationarity of the complement of S is preserved. Okay, and now the statement, you know, now we basically may look at a model which has S as a predicate, or maybe S is just the model. You know, there is, so look at the sigma 1 statement which says that S contains a club. This is a sigma 1 statement. So if the forcing axiom for this one forcing which we wrote down now were true, then this would mean that because you can force the truth of S contains a club, it's already true in the ground model, but this is nonsense because the complement is stationary. Okay, so the forcing axiom for this forcing, which is just epsilon away from forcings which preserve all stationary sets, it seems this is just plain wrong. So in that sense, in that direction, you cannot generalize Martin's maximum plus further. Okay, but there is also another way one could think of. One might be able to generalize double plus in that you allow more, dense sets to be met, right? So if you recall, what's happening here? Now I have something, shit. Now, okay, here we go. So recall that Martin's, you know, in Martin's maximum, we are supposed to hit LF1 many dense sets by a generic filter. So why not LF2, why not LF3? So what we want to do in the remaining time today is we show a theorem which I think is due to Foreman, Magidor, Schiller. Correct me if I'm wrong, is that Martin's maximum, you don't need the double plus here. It implies that 2 to the LF1 is LF2. Okay, so that means that the continuum is also LF2 as we discussed, and it also means that you cannot extend Martin's maximum in the direction that you hit more than LF1 many dense sets, right? Because if you were allowed to hit LF2 many dense sets, you can just look at cone forcing to add a new real, and then your, you know, as we had it yesterday, right? So you enumerate the cone reals in order to, you enumerate the reals of the ground model in order type LF2, and then the alpha then set just says that the cone real must be different from the alpha real, and you cannot hit all these dense sets, so that doesn't work. Okay, so a version of MM with more than consequence, a version of MM where you are supposed, or where not you, but the generic is supposed to hit more than LF1 dense sets is inconsistent. Okay, so there is a long history of using forcing axioms to prove that the continuum is LF2. I think this is one of the first and easiest arguments. There are stronger results, namely that you need only much less, a smaller fragment of Martin's maximum to prove that. So for instance, the proper forcing axiom also implies that the continuum is LF2, and actually the bounded proper forcing axiom also implies that the continuum is LF2. But I'm not going to go into that. Okay, we just want to see the flavor. Okay, so let's prove this theorem. How do you do that? That's a coding argument, right? We have to count the subsets of omega 1, and just counting things is always very difficult in set theory. We want to have some structure we can think about. So we have to turn the task into a structural task, right? We cannot just think about cardinalities. This is very difficult. We want to think about some structure. So what's the structure? So we look at the following set. So this is the set of all psi less than omega 2, which are limit ordinals actually of cofinality omega. Okay. So we define what a stationary subset of x to the omega is, and we define what a stationary subset of omega 1 is. And maybe I said something to the effect that we don't need other stationary sets, but that's not true. This is a stationary set. So that's a stationary subset of omega 2, and what does that mean? That's a notion of stationarity we did not run into yet. So a stationary subset of omega 2, that means that it meets every club, and the club in omega 2 is just a cofinal and unbounded subset of omega 2, so that every limit point of that set is also in the set, right? So that's hopefully a very familiar concept. So that's a stationary subset of omega 2. It's also very easy to see that it's stationary. But there is not Fodor, what I call Solovay, and I don't know if somebody else proved it before. The argument we gave for showing that a stationary subset of omega 1 can be split into LF1 many stationary sets shows that we can actually write this set as the disjoint union of omega 2 many stationary sets. Okay. Now, so what is the plan? So we have 20 minutes. So what I want to do is the following. So we want to do some kind of coding. So we write omega 1 as the disjoint union. We don't really need the full result. We write omega 1 as the disjoint union of TIs, I less than omega 1, there is no omega 2 here, each TI stationary. Okay, and we write as omega 2 as the disjoint union of SIs, I less than omega 1, each SI stationary. Okay, this is possible follows from what we just said. Okay, now what we want to do is the following. So we fix your favorite subset of omega 1, and it should be non-empty. So remember that we want to count the number of subsets of omega 1. We want to show that 2 to the LF1 is LF2. And counting the subsets of LF1 is the same as counting the non-empty subsets of LF1. Okay, so we fix the non-empty subset of LF1, and the aim is to find an alpha we want to find some kind of reflection point, okay? So we want to find an alpha which is now in the omega-1 cofinal ordinals below omega-2. Such that SI intersect alpha is stationary in alpha if I is in X. Okay. So okay. I just started realizing that there is no way that we're going to finish this in a quarter of an hour. Let me think. Okay, I'm proposing the following. I will, in order to prepare for tomorrow, I will write on the forcing which does the job, and then tomorrow we will start over again and finish the proof of this theorem, if that's okay, right? Okay. So, so basically, you know what, the plan is the following. We fix this splitting of omega-1 into omega-1 many pairwise disjoint stationary sets, and also we have the splitting of S omega omega-2 into this thing. And now we want to find a point alpha for a given X subset of omega-1. We want to find a point alpha so that if we look at SI restricted to alpha, then this is stationary in alpha if and only if I is in X. So what do we want to do? Basically, this means that if I is not in X, we want to have a club in the complement. Okay, and if I is in X, then this is supposed to remain stationary. So there is a natural forcing for doing such a thing. Okay, and the natural forcing is the following. Remember that we work under the forcing axiom Martin's maximum, right? So in order to show that something is true, or a sigma 1 statement, if you want, is true, it suffices to show that we can force it. But I will say more about this tomorrow then. There is a natural forcing to achieve this. And it's the following forcing. P is a condition if and only if there is an alpha less than omega-1, so that P is a function from alpha plus 1 into the points of cofinality omega, omega-2, so that this is a normal function. What is a normal function? It's a function which is strictly increasing, and P of lambda for a limit ordinal lambda is just the supremum of the P of xi's for xi less than lambda, right? Okay, and you want to have that for all eta less than or equal to alpha, and for all I less than omega-1, some equality holds true. And in order to state the equality, I have to go back to our X, which is a subset of omega-1, X non-empty. So what I want to have is an F, which is a map from omega-1 2 omega 1, so that X is the range of F. Okay, so what I want to say here is that eta is in tau I implies that P of eta is in S sub F of I, right? So the S sub i's, they are the split of S omega omega 2 into this pairwise disjoint stationary sets, and the tau i's split omega 1 into disjoint stationary sets. Okay, you want to have, you have omega 1 down here, you have omega 2 down here, and you start adding this function, so that if you have an eta down here, this function p sends it to some p of eta, and you want to have that if eta is in tau I, then p of eta is in one of the sets from the splitting of S omega omega 2 into pairwise disjoint sets, but where the index is in capital X, right? Okay. Okay, my suggestion actually would be to stop here, because when I start anything, it's going to take more than 10 minutes. And I think it makes most sense if I restate the theorem which I want to prove tomorrow morning, and then I will start out with this proof again and finish the proof, because it's going to take a little while. Is that okay?
Okay. Okay.
Yeah.